what is this FFT business that most of you have done the lab, and you've used the FFT. The rest of you will do it today. And that'll be the main part of what we talk about today. We have a command in MATLAB called FFT. What exactly is this? So to begin with, well, what is the answer? What does it stand for, first of all? Yes? Great. So this is the fast Fourier transform. All right, you've used this command in MATLAB. It's the fast Fourier transform. So to begin with, let's talk about finite duration signals. In particular, a finite duration signal, what I want to emphasize is it's equivalent to a periodic signal. So how is that? Well, notice that we can convert a periodic signal into finite duration one by just keeping one period. So let's say x of t has period cap t. So let's convert it to a finite duration simply by saying drop everything except one period. In other words, we'll have x bar be our finite duration signal, and that's just it's just the same thing as x of t, but for t in only the first period, like that. Okay? If it's discrete time, same thing. You just make it equal to x of n for one period. So here's n in the set 0, 1, up to n minus 1. So one period of it. And the point is that we could always convert this back to a periodic signal. Let's do this. And this process is called the periodic extension. So mathematically, we would say, let's define x of t equals a sum, an infinite sum, of this of its one period, this x bar, with shifts of distance cap t. Okay, so there's the periodic extension of a finite duration signal for continuous time. Discrete time is the same thing. All right, so this is not a complicated process. And we can draw an example here. Here's 0, here's cap t, and say we have some signal that looks like this. I'll draw it a little different here. Let's say. Okay, so this here is x bar of t. The periodic extension then is simply repeating this to make it periodic. dot, dot, dot. And you see for each, so this is just to see how the math matches up. Oh, where'd my hand tool go? Just to see how the math matches up, you see that for k equals 0, it's the green one. For k equals 1, you get this copy here. K equals 2, you get this copy here. K equals -1 is this copy here. Add them all together, you get the periodic extension. Okay, so this is periodic and consistent with x bar. So this sort of equivalence is going to be useful to think about, especially when we want to understand the DFT. So let's get back to Fourier series now. And we have a continuous time Fourier series, which we've already given the equations for this. But basically, it takes an x of t, which is periodic, and gives you back a set of coefficients, ak, for k equals -infinity to infinity. All right? And additionally, you have to record the period t if you want to be able to recover x. Okay? So the coefficients themselves aren't enough to know what x is. You also need to keep track of what period you're doing the transform with respect to. For discrete time, same thing. You get a list of coefficients that you can calculate by the formula. And you get a period n. So again, I just want to emphasize that this period here is an important part of the transform. You can't just record the coefficients and say that's enough to recover x. You must also know what the period is. I mean, just think about using the formula to invert it, right? You need to know n or t. All right. And we already saw that, in fact, for the discrete time Fourier series, we only needed, we didn't need all of the coefficients. Think again about the synthesis equation for the discrete time Fourier series. You only need the coefficients between 0 and n minus 1 to do the inverse. This is a property of discrete time only. For continuous time, you would need all of the coefficients. Okay. Yes?
For example, is it supposed to be
This up here? Yes. The endpoints, good point, because here I said inclusively. Well, for one thing, I guess we could look at this definition and actually do the addition. And the way I've defined it, you make a good point. Right at the end point, it would be the sum of these two, which might be somewhere like here, to correctly do this periodic extension. Turns out that isolated points of the signal in continuous time are not usually going to be a concern to us. So even if you redefine the signal at any arbitrary point to be something else, it won't be a meaningful change to the signal. So I guess that's why I wasn't too careful here. You could make this a open bracket to not have that problem. Good point. Okay. All right. So let's go up a little bit here. So that's the Fourier series. Now this so-called discrete time Fourier transform, or not discrete time, sorry, discrete Fourier transform. This is a phrase with meaning all in itself. Discrete here actually refers to both discrete time and, as we'll see, discrete frequency. But what you should think of this as discrete time and a finite duration. But anyway, it's just a phrase with a name, and what the name means is it's a transform that takes a vector x and gives you back a vector we'll use A because we're using A for the coefficients above. So it takes a vector and returns to you a vector. Now, these vectors are both the same length. And furthermore, you should think of this length as encoding the period. Okay, so in other words, the vector x is a vector of the signal at value at time 0, at time 1, ... all the way up to time n minus 1. Assume the period is length n, or the period is cap n. And so this vector is one period of your signal. And the transform returns to you a vector of a's of the same length. The length of the vector tells you the period, so it sort of avoids this technicality above where I had to say the coefficients and the period. Well, it just is given to you in the length of the vector. Okay. Now, this DFT is essentially the discrete time Fourier series. I'll define it precisely in a moment, but really you should think of the DFT as the discrete time Fourier series. All right? Because if we think back to the Fourier, let's look back at the discrete time Fourier series on our way to defining this discrete Fourier transform. Let's consider the discrete time. Discrete time Fourier series for a special case of just length 4, period of length 4. All right. Now, we have our formula, which I'll repeat here. Here's how you calculate the coefficients. But if you plug in n equals 4, it's precisely the following. Okay, so here's how you calculate the coefficients, but we can write that out. There's only 4 of them that we need. Remember, we only need the first 4 to do the inverse. So that means A0 is 1/4 times, and if we put in k equals 0 into this formula, then this exponent is 0 everywhere. So this is just a sum. Those are 1s. It's just a sum of xn. So x0 plus x1 plus x2 plus x3. So that's the first coefficient. It's just the average. All right. A1 is going to be, now we don't just get an average. We plug in k equals 1 here. We get a pi over 2. Okay, we combine all this stuff together. Can't see, yeah. You get a pi over 2, so it's e to the negative I pi over 2 times n. Of course, that means for the first term, n is 0, so it's still just x0. But for the next term, that exponential function is e to the negative I pi over 2. Well, that is just negative I. Okay, we know how to interpret that number. And then the next one is just, the coefficient is negative 1 that you multiply by x2. Again, I get that by just saying, well, this is n equals 2 in this sum. If I put a 2 in there and I have another 2 over 4, all of the constants cancel. It's e to the negative I pi, which is negative 1. Okay? And then here we get plus I x3. Okay, so I get there's the formula for calculating A1 explicitly in this case. Let's do the last two. This just becomes very simple. This is x0 minus x1 plus x2 minus x3. right, nice. And this one just becomes plus I x1 minus x2 minus I x3. All right, so that's how we would calculate them explicitly. Now notice, well, let's just look at an example to drive this home. So suppose xn is the following signal. It's 1 when n equals 0, 1 when n equals 1, 1 when n equals 2, and 0 when n equals 3, and it's periodic. Period 4. Okay, so that we can stick with our formula we derived here. Okay, so what that means is it's the periodic extension of what I've just defined here. So here's 0 in time, and our signal is simply 1, 1, 1, 0, 1, 1, 1, 0. If you go back this way, 0, 1, 1, and so forth. That's the signal, this periodic thing. And we want to calculate the Fourier series coefficients for this. And we would just plug in, we would get A0 equals the average. So it's just 3/4. A1, plug that in, the first and third term cancel, and you just get negative I over 4. A2 is just 1/4, and A3 is I over 4. All right, so those are we just explicitly worked through the example. All right, we have these coefficients. You interpret these as saying, each one of these tells you the constant you would have to multiply by the exponential of a given frequency. All right, we'll come back to that idea in a moment. But you can interpret these if you want. So you can say, oh, look, the largest one in magnitude, at least, is the first one here, A0. Does anyone want to interpret why is the largest one in magnitude A0 for this particular signal? What does that have to do with this signal? Yeah, so a zero frequency, if you interpret this, again, we'll come back to this, but if you interpret this as being the component, the zero frequency component, or zero frequency component in the Fourier series is just a constant, okay? And so this is saying, well, if it was a constant, it would only have this component. This isn't a constant, but it's kind of close. It just, deviates a little bit. So the largest component is that zero component. Okay. Now, the point about this exercise actually is to show that we can express the above in matrix form. So that is that A equals 1/4 times, let's make that bigger, this matrix, 1, 1, 1, 1, 1 minus I minus 1 I. Whoops, that's not 0. 1, negative 1, 1, negative 1, and 1 I, negative 1, negative I. Okay. So, and it's that times x, right? So this is just a compact way of writing this set of equations right here. Right, so really, the discrete time Fourier series is just doing a matrix multiply with a square matrix. All right. Now let's notice that, okay, this here, we'll give it a name. We'll call this I'll put brackets around DTFS and put a little sub 4 to mean this was of length 4. We'll give that the name of this matrix, including this 1/4 out in front. All right, so just so we don't have to rewrite it every time, that's the name of this matrix. Now, we can do this in general, not just for length 4. And we can say that to express this matrix, it's going to be convenient to just define a variable. We'll call it capital W sub n. And this variable is just a number. It's just e to the I 2 pi over capital N. Okay, so it's one of the nth roots of 1. All right, it's, just go a phase of 2 pi over cap N on the unit circle. That's what this number is. The reason I define that number is simply to express a matrix without so much clutter. Consider this matrix. Okay, so I filled out a matrix where the first row is all this constant to the 0th power. Well, to the 0th power, that's just 1. So this first row is all 1. Okay. The second row is that constant to a power that increases as you move along the row. All right. And the third row increases by steps of 2 as you move along the row. Fourth row would increase by steps of 3 and so forth. Yeah. Okay. Now, so this matrix here, and this is going to be an n by n matrix. So I guess I should put the corner so you know how far do we go in each row. Let's say way over here is, you go all the way up to w n to the power of n minus 1. Okay, so it's an n by n matrix. Okay. Now, notice with this definition, let's give this a name. This name is going to be kind of a, I just invented this name here that I'm going to call it, and it's not very pretty. We'll say it's the complex exponential matrix. Okay, why would I say that? And we'll use the sub n there. All right, just to give it a name. All right, why is this the complex exponential matrix? Yes? Yes, you're right. Thank you. Yeah, this here is still to the 0th, and this one here is to the n minus 1. Good. Thank you for that. Okay, so why would I call this the complex exponential matrix? Any ideas? Because every row is a complex exponential, discrete time complex exponential. This function that we use in the Fourier series, right? It's just raising. It's the magnitude of any number in this matrix is 1. Okay, but the phase is just cycling as you go across the row at different rates. In other words, if you took any row of this and considered it a signal, it's exactly that complex exponential signal we've been dealing with the Fourier series. So notice that this thing here has a nice property that its transpose is the same as itself. So it's transpose symmetric. Okay, you probably noticed that already. In other words, you get the same thing here as you get here. You get the same, you just go diagonally across the matrix and you get the same value on its transpose point. Okay. So with this definition, then we get precisely that the Fourier series, as we derived above, the discrete time Fourier series of length n is just 1 over n times this complex exponential matrix, however conjugated, right? Because if you look back up here, well, here we put in specific numbers, but if you look at the formula that we got everything from, there's a negative in the exponent here. So if you just take this formula and from it define the matrix, which is essentially what we're doing, from that formula we're getting a matrix, they would have negatives everywhere in the exponent. Well, we get the negatives by putting a conjugate. Okay, so this is the discrete time Fourier series. It's exactly that operation. The inverse of it, the inverse is the other equation, the synthesis equation that gets us back to our signal. That is actually exactly this complex exponential matrix. Okay, so here are the two formulas for the discrete time Fourier series in matrix form. Now, the so-called discrete Fourier transform, here I'm finally going to give you the actual definition of it. And it's just the following. DFT for length n vector is this complex exponential matrix conjugated. And so therefore the inverse DFT is 1 over n times this complex exponential matrix. So you see, I said that the DFT is essentially the discrete time Fourier series, and even in its most precise sense, the only difference is where you put the 1 over n. Now, if you saw how we first described the Fourier series, it sort of makes sense to put the 1 over n on the analysis equation because we want to think of the synthesis as the main part, getting back to x from our coefficients, and we put that in the simplest possible form, which means we don't have a 1 over n in the synthesis equation. All right? But there are reasons to also want to do it the other way. It really doesn't matter, obviously, right, which one gets the scaling constant. But that is the only difference between these two transforms. And the fact that the DFT, you usually think of it on vectors, on finite length signals. Although, as we saw, it doesn't really matter. Any periodic signal is equivalent to a finite length signal. Okay. Quick linear algebra note, just for those that care. If you put 1 over root n, notice I put a 1 over n on either place. I could have put a 1 over root n on both. So this matrix here is unitary, which means that its inverse is the conjugate transpose. That should be clear from what we just saw above. And unitary matrices are usually thought of as a change of basis. And this change of basis diagonalizes Toeplitz matrices. So that's a little aside, and I actually don't expect that to be meaningful to everyone. I don't care too much whether it is, but if you know how to interpret that and what it means to diagonalize a matrix, it's a foreshadow of things we're going to learn about the Fourier transform, in particular convolution. Toeplitz matrix is like convolution. But don't worry if that doesn't mean anything. Okay, so now the fast Fourier transform. What is this fast Fourier transform? Well, notice that the DFT, which we were just introduced to, is, what is the, okay, so it's an n by n matrix multiplication. Right? So how long does it take to perform this calculation. You have some technology that's going to compute a DFT of some numbers. What's the complexity of doing this? Matrix multiply. So it would be n squared. Complexity if it had no structure, and so let's just put that down here. A general n by n matrix multiply is n squared, and you can think of it as, of course, you've got to do one multiply for every entry of your matrix. Then you do some sums. But that means that if your vector is getting very long and you want to do a DFT, you're going to be waiting per sample, you'll be waiting length n time to get your DFT. In other words, it's kind of a bad complexity. It would keep you from doing very long vectors, from calculating DFTs of very long vectors. All right. So the FFT is just an algorithm to do this in n log n complexity. So it turns out that the structure of the DFT matrix, which, as we saw, has a very nice structure, you can take advantage of that and actually do this matrix multiply in n log n time. There's many ways of showing that this is done. There's diagrams, butterfly diagrams, and stuff. This was developed by Cooley and Tukey in the 60s. And actually, this had huge impact on DSP. Okay, because now, in a very reasonable amount of time, n log n, usually you think that's not too much beyond just linear time, meaning you don't pay too much for long vectors. Of course, you would expect at least linear time. Imagine you have some signal. So here's what you're considering to do your signal processing. You have some recording, some stream of numbers coming in from some sensor. Maybe it's a microphone, right? And you want to do some processing, and sometimes that processing, what you usually do is you're going to record a segment of time, and you're going to process it. Now, if you go to twice as much time, of course, you now have twice as much, you have the luxury of having twice as long to do the processing, if you want to do things in real time, let's say. Under n squared complexity, that's still, you're going to be limited by how long you can do it. But here under n log n, if you say, well, that's not too much beyond n, we now can take very long samples, do a DFT if we want to as part of a step of our processing, and still kind of scale with real-time applications. You're still going to be limited to how long of a DFT you can take, but not as limited. All right. Now, just a quick note of why this works. I'm not going to go through. Some of you in algorithms classes here will do the FFT. I'm just going to show that the structure of the DFT. See, the point is it factorizes into simpler matrices that you can then do computations faster on. So I'll just give you the example for n equals 8, just a rough idea. The DFT, let's change the color. DFT 8, well, we saw that we could represent it as the square matrix, the complex exponential matrix, but we can also factor it another way into 3 different matrices. Here we have, the first one is like 4 matrices put together that each are diagonal. So this is just the identity matrix. I'm going to just put a big 0 on the off diagonal. That means everything else in this 4x4 segment is 0. Okay. You get the same thing here. Identity matrix down here with zeros. And up in this corner, this 4x4 segment we'll use this W notation. And down here, Okay, so we've got the first part of this factorization. I'll put little lines here to represent its collection of 4 different simple matrices. Whoops, blue. Now, the next thing is we do a matrix here that is in fact DFT4, 0, 0. And then the last part is also a simple matrix, something that just like rearranges the terms so it looks like this. Okay, so it turns out if you multiply all this stuff out, I'll do this too, then you would get DFT8. And this type of factorization works for any power of 2. All right, so you always can do the Fourier transform by doing one of smaller size, all right, of half the size. Now, even this, there's some savings. You don't actually have to do each of these. First of all, these matrix multiplies individually are much easier than a general matrix multiply. Doing a diagonal matrix multiply is very fast. Secondly, there's a lot of overlap, like that and that. Those are the same. These are the same except negative. So you don't actually have to do these calculations twice. And so when you put all the bookkeeping together, you find that you can utilize this DFT of half the size in computing the one larger and so forth. And so you end up getting an n log n scaling. Okay. All right. Next thing I want to do is talk about how to interpret these coefficients of the Fourier series, which, again, many of you have done the lab already. You've used FFT. You've plotted the coefficients and tried to get some interpretation out of them. Let's just talk about that process a little more carefully. And to begin, we should look at something called aliasing. Okay, this is a purely discrete time effect. All right, and what this means is that 2 sinusoids can be the same in discrete time. Even though our formula, even though it looks like in the math we've defined 2 different sinusoids, they in fact can be exactly the same. Let me give you an example. Here's a sinusoid. Okay. What's the frequency of this sinusoid? It's 1, right? Because the form with frequency would be cosine 2 pi f t or n. All right. So this is a frequency 1 sinusoid. But let's consider discrete time. Discrete time means n is an integer, right? So n is only an integer in discrete time, and anything that happens between that is meaningless. It doesn't exist. Okay. So then I claim that this cosine of, well, let's find the sequence. Let's call this xn. What's x of 0? It's 1. What's x of 1? What's x of 1? 1. X of 2? 1. Okay. Wow, it looks like cosine of 2 pi n equals 1. These 2 signals are equal. 1 is the constant signal, the 0 frequency cosine. They are, in fact, equal because we're only looking at integers n. So these are the same thing. There's no point in making any distinction between these. All right? And this isn't the only example where that's going to happen. To see that in picture, by the way, just to get some idea what happened here. Well, of course, our formula gave values even in between the integers. But the formula was just a concise way of representing this discrete time signal. The discrete time signal is really just at the integers. So you have, you're here, 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 and it didn't matter what the formula said in between, right? And so this is the same as just saying 1, all right? Now that happens in general, and to see it by equation, you just have to realize that e to the I 2 pi f1n equals e to the I 2 pi f2n, all right, if the difference between the frequencies is an integer. So now when we have these complex exponentials, and remember, negatives and positives are different sinusoids, right? Different complex exponentials. If their frequency differs by an integer, in discrete time, they are exactly the same. All right. So these are both signals, and they're the same signal, because for all integer n, they're the same. Now, mathematically, we can just say, let's verify this. Why is this true? Well, because e to the I 2 pi f1n over e to the I 2 pi f2n equals e to the I 2 pi f1 minus f2n, which we said is an integer. f1 minus f2 is an integer. So, of course, e to the I 2 pi integer times n is 1. Okay, so there we go. Aliasing. This is the important formula for aliasing. We're going to come back to this notion of aliasing because it's in signal processing. This is referred to a lot, especially in sampling, which is a topic we'll cover. Aliasing becomes an important consideration. But for now, just think of it as this formula. And here's an example just to illustrate how this happens for other sinusoids as well. Okay, so here we have one sinusoid of a high frequency in purple. But notice where the integers are, 0, 1, 2. When you sample it at only the integers, okay, this blue curve is a different frequency sinusoid that exactly matches all of those points. Okay, this will always happen. What I mean by that is even if we change the frequency, we'll be able to find two cosines that match. More than two. There's a whole bunch that match at the integers. Okay, this is just showing you two that will match. So these two sinusoids are just aliases of each other, all right, in discrete time. What that means is that if we go back to our all right. What that means is, let's go back to our example above where we had the DFT of the discrete time Fourier series, where we had this signal that was x. I'm going to repeat x of n was 1, 1, 1, 0 for n equals 0, n equals 1, n equals 2, n equals 3. And we calculated the coefficients. A0 equaled 3/4. A1 equaled negative I over 4. A2 equaled a fourth. Positive a fourth. A3 equals I over 4. Okay, so we calculated this out. Now it turns out that if we wanted to keep calculating coefficients, the formula tells us how to calculate any number of coefficients we need. We just stopped at 4 because we knew we only needed the first 4 to do the inverse. Okay, but it turns out that if you kept going and you calculated A4, the formula would be A4 equals 1/4 sum n equals 0 to 3 of xn e to the I 2 pi e to the negative I 2 pi 4 over 4 n. Okay? But we notice that that equals, by aliasing, we can change the frequency of that exponential to 0. Okay, which equals A0. So in general, A sub k here, when n equals 4, we're finding that if we plug in the formula for AK, same process, we would get that it equals AK minus n due to aliasing. In other words, this complex exponential that's in our sum, if we switch it to a complex exponential of another frequency that we've claimed is equal through aliasing, then we can derive that in fact these coefficients are equal when they're separated by n. What does that mean? What does that mean about this sequence A? What was that? Repeats. So we call that periodic, right? So AK is periodic with period n. Wow, that's the same period that x was periodic with respect to. So if you have x with period n, you calculate Fourier series coefficients, they're also periodic with period n. No wonder we don't need to keep all of them. No wonder we only need the first n in order to do the inverse. Because in fact, they're just totally redundant. Okay, again, this is only for discrete time. None of this aliasing stuff happens in continuous time. All right. So in particular, last thing I want to say about this is that if you interpret these A's by their corresponding frequency, what we would do, one interpretation is to say this A is associated with a particular frequency, and that frequency is f equals k over n. Because if you look in the formula, the part where frequency goes in the complex exponential, you have k over n in the Fourier series formula. Okay? So then that means that this frequency here is f equals 0 to go with this coefficient. F equals 1/4. F equals 2/4. F equals 3/4. So what we have from the Fourier series is some coefficients associated with a collection of frequency terms. Okay. You'll notice, I want to explain what this FFT shift does, and maybe I'll revisit it next time, but it's simply noticing that due to aliasing, this coefficient, we know that A negative 1 equals A3. Okay? We know that A of negative 2 equals A2, right? So again, the frequency interpretation is that this coefficient here isn't just, A2 is not just f equals 2 over 4, but you could also interpret it as f equals negative 2/4. And this term here, you could interpret as f equals negative 1/4. And I'm trying to rush it too much. The FFT shift simply rearranges your vector. Takes the second half and puts it before the first half for exactly this reason. I'll talk about it again next time, but you can think about it yourself and figure it out if you want from your experience in the lab. Okay.